So if we summarize and we put together all the different steps that we've seen before, we have this algorithm. If I have a robust optimization problem where everything is linear, except there is a bilinear term in the disturbance and the constraints, it depends bilinearly on both, then I can get rid entirely of the robust part by replacing every robust constraint by one different constraint where I have introduced one vector of dual variables corresponding to the optimization problem, the auxiliary optimization problem that's derived from this constraint. So we keep, of course, all the optimization variables we had before, and then for every constraint, we add a vector of optimization constraints. And one way to remember the size of this vector is that this vector will be multiplied by the C, which is the right-hand side of the constraint on the disturbance D here. So every lambda j has the same dimension, which is the set of constraints, which set of inequality constraints we have for the disturbance variable D here. So two things about this. First, it's important to know this recipe and able to immediately detect the difficulty of the problem you have. If you have robust constraints, if they're separable, things will be easy. If they're non-separable but bilinear, then you will have to work a bit by adding these dual variables. That's the first thing. The second thing is also to realize how we were able to do this. Well, it is by doing duality that transformed the mean that correspond to a certain quantifier into a max that corresponded to the opposite quantifier. And the opposite quantifier, when if it's there exists, then it can be simply leading to adding more variables. The second technique is used much more generally than in the setting we have here, but that's already enough. Now let's see. If we apply this to this simple example here, I have a very simple example where my optimization variable is of dimension 2, UV. My constraint is of dimension 1 here. How many dual variables do I add to this problem if I want to make it robust, to remove the quantifiers? I close the poll in a few seconds. Closing. And the majority says B, which is the correct answer. The trick is to remember that the dimension of every Lagrange multiplier is the dimension of C, which is the number of inequality constraints. Here we have two inequality constraints on D. We have two bounds, so two inequality constraints. And if we do it exactly, we'll see, therefore, that we will have Lagrange multiplier of dimension 2, I call it lambda mu. And that will give me exactly this here, with two constraints, with those constraints on lambda and mu by writing the dual problem here. So it's, of course, not quite intuitive how this relates to that. So when, at least here in the small case, we could make sense of this, but in a larger setting, of course, the problem that we have becomes very abstract. But we know here that I've completely removed the quantifier from this problem. Here's a question which is perhaps not strictly necessary, but it's just to show you what you have learned today, how powerful it is. the statement that I'm writing here, the statement is a condition on C. So C is a vector of dimension n. And I'm saying C satisfies the following property. C times x, the inner product of C and x, is less than 314 for every value of x that satisfies some constraint here. This is a generic form of a convex piecewise linear set. So I'm not specifying what the matrix A, B are. So I say for every x that is in this set, that I assume is quite generic, I think that I put the statement C times x, the inner product of C and x is less than that, which means the size of C, the norm of C multiplied by the norm of x multiplied by the cosine of the angle of the two is less than this for all x that is in this polytope here. So this statement, I propose three equivalent forms. The first form is saying the max of the inner product of Cx over all x that satisfy those constraints is less than 314. Right? There exists a lambda that satisfies those constraints such that, so m is the size of the vector b, such that, because we have the inner product of b and lambda here, that satisfy those constraints here, or for all lambda that satisfy those constraints, b inner product of b and lambda must be less than 314. It seems completely abstract, but with what we've done, it's fairly simple. With what we've seen, it's fairly simple. I close the poll in a few more seconds. Closing. And the majority says D, which is exactly correct. Well, what is obvious and easy is that A is true, because here we're saying the number 3.14 is larger than that for all value of x. So we are in the framework where we're saying an expression is larger than all values of a certain set. And we know that this is equivalent to being larger than the max of all those values. So the max, the dummy variable is x, it's the max over all x that satisfy those constraints. So A is the usual transformation that we have seen here, that we have seen of removing a max versus a quantifier. B is true also. This is a bit less obvious. For that, we need duality, because now we transform this maximization problem into its dual. Now, because it's linear and under mild condition that this set here is not empty, the dual and its problem are equivalent and they have the same optimal values. And the dual, we find it by our cheat sheet that we have seen a few minutes ago. The dual is the minimum of B lambda such that A lambda is larger than C, lambda being non-negative. So again, we see that the constraint B becomes the coefficient and the coefficient becomes a constraint here, and the matrix of constraint is transposed here. So in this generic form, it's fairly simple, not entirely obvious, because max becomes mean, larger than becomes less than becomes larger than. So those subtle things are embarrassing, and that's why we need a cheat sheet. but this is what we obtain here. So that means that this condition is equivalent to 314 being larger than this mean here, because the optimal value of this problem is the same as that here. But saying that 314 is larger than the mean means that 314 is larger than one of the values here, which is statement B. Statement C, because the quantifier is wrong, is of course not equivalent. So what we have seen with that is that the theory of, or the framework of Boy and van den Berg explained everything. This theorem that we saw here is known as Farkas lemma. This is the equivalence between a statement of this form and a statement of the form B here, and is used, for example, by linear programming solvers to solve in practice linear programs. So what I want to illustrate with that is that with the generic form of Boy and van den Berg and the simple universal statements on duality, we can explain quasi everything that is known in textbooks and often takes very different forms. Well, but the true intention of this is to be able to apply a form of control, which is called affine disturbance feedback here, which is something very, very frequently done in energy systems, in general in engineering, because affine rules, control rules are very simple to engineer, and we know how to make them work, as we will see now. So recall that last week we started when the loads are known, and we found how to solve exactly for the values of the optimal loads, of the optimal generators. Then we started saying, yeah, but if I introduce some uncertainty bounds, then I can compute the set points, G1, G2, G3. We have seen that we can solve for G1, G3, and G2, G3, and G1 will follow implicitly, at least with the DC approximation. But when we did that, we did only a simple game where I choose the set points, nature reveals the disturbances, the true value that I didn't know, and then I stop. But of course, it would be better if instead of that, I could react to the changes. But how do I react to the changes? Of course, I don't want to redo my problem in real time, although that's also an option that you can do at least in quasi-real time. But if I want to do it in advance, I have to pre-program a control law. So a control law, or in general, is called a policy. So if I can adapt in real time by whenever I observe that the load takes a value that is within the bounds here, the values of the set point will follow exactly, will find exactly the value that I have. So a feedback policy, a policy in general, is a system where we adapt to the disturbance and adapt the values of the control variables. Linear control laws are what is called affine disturbance feedback control. Affine disturbance feedback control consists in saying that when I know exactly the values of the load, which I will know only in real time during execution and deployment here, the values of G, of the generator here, will automatically be adapted to become, for example, a linear term, V2 times the sum of the loads. In general, I could have a more complex expressions where I don't have a single V2 in front of every load, but I could have different parameters. I will have a matrix instead of a single number. But to keep things simple in this expression, I assume I have a single number here. So I assume the value of the generation here is a constant plus a term that depends linearly on the total load that is to be run in this network. That's the simplest form of control law, and it's called a linear control law. It's called affine disturbance feedback control. Feedback control because we derive the control, the value of G2, as a function of what we observe in terms of the disturbance, and affine because it's an affine function. Again, here I show it in the very simple case where we have just two numbers, U2 and V2, but in general, if I would have larger matrices, the theory that I show will work exactly the same way. Now, this is, of course, very, very different from what we said before, because now I'm much more powerful in the sense that I still do the computation ahead of time, but what I compute ahead of time is U2 and V2. I don't compute G2. I don't compute the generation that G2 will have to produce. I just say, what are the parameters of the controller? In this simple example, I assume that G3 will need to be computed ahead of time and only G2. As you can easily imagine, we will do that at every generator. How is that done in practice? Well, very often generators are equipped with feedback control. Feedback may come from many measurements, but here you can imagine that you measure in real time, for example, every 100 milliseconds, you measure with PMUs or with RTUs, you measure the load, and then you send that over a communication network to G2. And then the value of L1, L2, L3 is fed to change the set point of the generator G2. So that would be a very simple way to implement this. Now, if I am in the same framework as before, I have some uncertainty on L1, L2, L3. If I assume that the expected value of L1, L2 is L1 bar, L2 bar, L3 bar. Once I have chosen the control U2, V2, the forecasted or the expected value of the generator will be given by this formula here, which is simple because everything is linear here. Let's work and see how we can put everything into our example here, those ideas into the example here. So now I assume I want to set G3 fixed, and for G2, I want to find the values of the control U2 and V2. So now the control variables are U2, V2, and G3. As before, the state is all the variables that result from the disturbance and the control. That's the angles with the DC approximation, and the G1, which is the resulting value of the slack bus here. The forecasted value of G2 is given by this here. If I assume L1, L2, L3 are within bounds and have a mean value that is as before. Of course, the actual value will be depending on the disturbance. We don't know what the actual value here. If I want to apply the simplest of the framework we saw before, I will optimize the expected cost. So I will not optimize the worst case. I could easily do the worst case. Here I do the expected cost. Well, then we have the expected value of G2, which is given here, depends on U2 and V2. That's the value we saw before. For G3, doesn't depend on the control parameters because we control G3 directly. And G1 will derive by the equation of total power. That gives me the value of G1 here. So we have an expected cost that now depends on the control parameters as before. So here, not much difference. Similarly, the constraints. Well, in the constraint, I eliminate the state G1, theta 2, theta 3 in all the constraints that I had. I had control constraints on G1, that gives those two inequalities. I had constraint on the power flow on line 1, 2, that gives those two inequalities. And here I have eliminated all the state variables as a function of the control parameters and the disturbance here. Of course, that requires some work to do. I've done the work, and here is what I've obtained. It's very similar to what we had before. With one major difference here, we see that we have a robust problem in the sense that we have the for all L1, L2, L3. So we have a quantifier in constraints, and the variables are not separable, but we have a bilinear term. So we fall into the category that we had before, and therefore we can transform the problem into a non-robust problem by adding supplementary variables here. For example, the first constraint is this one here. I add one vector of Lagrange multiplier. Remember that the dimension of the Lagrange multiplier is given by the number of constraints on inequality constraints on the disturbance. So here I have 6. So my vector is of dimension 6. So I add for one inequality, one vector lambda 1, and I create the dual problem. And this constraint that for all L1, L2, L3, this inequality is satisfied is equivalent to this inequality here, where lambda 1 to lambda 1,1 to lambda 1,6 satisfies all the constraints that are derived by constructing the dual of this optimization, of the auxiliary optimization problem, which gives this constraint here. If I do that in general, how many inequalities will I need to massage? How many auxiliary problems will I have? And therefore, how many Lagrange multiplier vectors will I add to my problem? I close the poll in a few seconds. Closing. H is the correct answer, 10. We have 10 variables. We have 10 inequalities that have this bilinear combination of the disturbance and control variables, 1, 2, etc. 1, 2, 3, 4, 5 times 2, that gives 10 inequalities here. So we need to add 10 vectors of dimension 6 each. Right? So we add 60 additional optimization variables. That's the price to pay here for removing those disturbances here.
Sorry?
Yes?
Why did you say dimension 6 each?
Well, because you've seen it here. The one vector of Lagrange multiplier has dimension, which is given by the number of inequality constraints of the disturbance. We have 6 inequality constraints. We have L1 larger than 0.9, L1 less than 110, L2 larger than, etc. So we have 6 dimensions for the 6 inequalities for the disturbance D, which is L in our example here. So every lambda is of dimension 6, and we add it 10 times.
Okay, thank you.
You're welcome. Let me skip this one. So if we, let's move, sorry, Pluton, so let's move to the slide 68. If we put all of this together now, if we look at the global optimization problem that I have to solve my robust problem with affine feedback, how many optimization variables do I have? I close the poll. The answer is 63. we've seen that we added 60 variables to remove the for all quantifiers. And then we had the 3 original variables, U, V, and the G3. So that gives 63. So in this very simple control system where we're controlling only one of the generators, and the control law has only one common gain for all the loads, the dimension becomes 63. If we add more control, we will have probably we'll be getting closer to 70. So the price to pay is essentially the removal of the robust constraint here. That's the cost of robust optimization. So it's a technique that is quite often used, but of course it amplifies the size of the problem. This is why very often we insist on having linear problems, because with linear programs, we're able to handle large problem sets with large dimensions of the set of variables. With more general convex problems, this may become a problem. This is why we very often stay with linear versions of things. So let's apply this numerically to our case. We saw just an hour ago what we do if we do static control. So we simply compute the optimal value of G2. Now, if I add a control law on G2, I obtain the red curve here for the cost when we vary the uncertainty of the load here. So we see two things. We see the cost is less, not much less in this example. Now it depends on the case studies. In many cases, it will be much less. In this case, we do a simple control on G2. If we would do a more sophisticated control where we control separately L1, L2, L3, and we do it on G2, G3, then we would have something that is distinctly better. But more importantly, we see also that the optimal control here has a broader range of applicability. We saw that when the uncertainty became 100, the static control stopped working. It did not find any solution because there was no feasible set. It was not possible to control in advance G2 and G3, but it is possible if we have a feedback law, we can double the applicability, the place where the uncertainty becomes too large is double here. So we can see that we can apply practically over the whole range here, because when we get to 0, then we are outside the feasible region. So we see that with the controller, we're able to compute an affine feedback disturbance control policy that works across the whole range of uncertainty. And we'll see also that the values that are computed, how they vary over time here. We see that they vary in a completely non-monotonic way, which is exactly what we wanted. We want this grid to adapt here. So the feasible region is much larger and the cost is less. Of course, you need to work a bit more to do it, but I would say this is the state of the art of controls, at least for linear controls. What we will see in 2 weeks is nonlinear controls using the technique of MPC. That is, I would say, the other component of the state of the art. But for now, we will stop on this important set of techniques that we have seen today. Today, we focused on handling uncertainties. The important thing is how to be able to transform my problem that has uncertainty using the generic framework of control and disturbance. We've seen there are many variants. We focused on some. We need to make a philosophy, make our mind on what we call cost. Sometimes people take the expected cost. That's what we will do in the labs because this is very often the simplest one. Sometimes we can do also the worst case cost because this leads to simpler formulations, often in particular when the disturbances are not, the distribution of the disturbances are not known or not easy to manipulate. We have seen also that invariably, this leads to constraints that have quantifiers of this form here. And if they are separable, that's easy. We simply solve one optimization problem for one constraint because the value will not depend on U. If it's not separable but bilinear, then there's a systematic technique using duality. It works in other cases, but in practice, that's the most commonly used case. Already this case is not so simple, but hopefully now you master it. And then the take-home message is also, it's always better to compute an optimal policy than an optimal control value. An optimal static set point is, of course, not reacting to changes. And as soon as the uncertainty is not minuscule, the cost to pay for that will be large here. And we have seen how affine disturbance feedback lends itself very well, doesn't break the framework, it just gives the same kind of technical problems that we had before here, and can be solved efficiently by linear programming. Voilà, that's the end for today, at least for the lecture part. I guess you're busy with the lab. So the current lab that we have on OPF is based on the theory we saw last week. So the theory that we saw today will be necessary for the lab, for the following lab, the lab on demand response and OPF, that we will do only a bit later. So there is also for today and for this week, there is also a quiz on this part. So I encourage you to do the quiz before. The techniques that we have for optimal feedback, affine feedback policies is not very, very simple, as we have seen today. So I think it's interesting that you go through the quiz and you verify your understanding this week so that you get well prepared for the applying it in the following week when the lab will start next week.